Okay, so I think let's go ahead and get started. We're excited to present to you session 2 in the Greenhouse Generative AI training series. And so in this session, we'll be covering example use cases. And we'll kick it off with Laurent, then Jordan, and then with Amit, Amal, and Aditya. So with that said, I'm going to pass it along to Laurent, and he can take it away. Thanks. Enjoy.
Thank you, Feda. So I will share my screen. Okay, can you see my screen?
Yes.
Yes, sir.
Okay. So hi, everyone. My name is Laurent Kerel. I'm a distinguished engineer at F5. And today I'm here to talk about a project trying to derive value from bug using generative AI or large language model, in my case. So this presentation is relatively brief, less than 15 minutes. And my primary goal is to explain my ideation process behind this small side project that leverages LLMs. I will be covering the different steps and decision and constraints and challenges encountered in this particular type of exploratory project. Okay, so to begin, we can ask ourselves how ideas come about. And for this particular project, the idea came from a specific question, as it's often the case. And more specifically, the idea was originated from a question posed during an executive leadership meeting that Gilad Brasha and I attended a few months ago. We were discussing Rust and memory-safe languages in general. And one of the questions was, could you gather evidence that memory-safe languages significantly reduce the number of bugs in F5 products? So the short answer is yes. We do have some form of evidence recognized by the industry that memory-safe languages can help reduce the number of bugs in complex software. So for example, 70% of Microsoft vulnerabilities are due to violations of memory safety. And similarly for Google, we have 99% of Android vulnerabilities, also due to violation of memory safety. But if you think about it, the greatest value these companies derive from these studies is not the numbers themselves, but rather the process they establish to continuously improve their understanding of their development process, and consequently how to improve them, or if we improve the development process. But that's precisely what this project aims to address. And I believe that with large language model, we now have a credible option to process complex bug description in order to better identify recurrent issues and weaknesses or bad practices in our dev process. I think we can also collaboratively enhance the overall software development lifecycle and vulnerability management. And finally, with this project, I think, and importantly, I think we can assess the impact of tools and languages on the quality and security of our product. So assessing a new static analysis tool or accessing a new language will be much easier with such system. So these are just a few examples of what we could achieve and automate, and I'm sure more will emerge as we progress. Before we look at the different stages of this ideation process and how to build such project, I will just remind you that it's key to keep an open mind, because any question can lead to an interesting idea, and that's a typical example of it. So typically the first step when you have an idea is to recognize the type of problem you want to solve. And in this specific case, it will be interesting to clarify First, what a memory safe language is. And to make it short, memory safe language is one that prevents basically certain class of bugs, such as memory leak, buffer overflow, double free, and to some extent, also some concurrency issues like data races. So now imagine that you have a complex bug description, and you have a system able to assign or to predict that you have one of these class of bugs that are corresponding to this bug. Then you are able to answer the initial question. We have a certain percentage of bugs in our system that are related to memory issues or concurrency issues. So the outcome of this first phase, the problem recognition, is that the problem that we are trying to solve is basically a classification problem. A classification problem on unstructured text. And it's one of the tasks where a large language model excels at. So the next step is to identify available data. And in this specific case, the most obvious data sources will be obviously Bugzilla and NGR. However, we can also take advantage of public information and other publicly available classification efforts. And an example of that is the common weakness enumeration, or also named CWE, which are essentially codification of well-known types of bugs. So that could be useful also for some improvement into the system, like fine-tuning, as we will see later. And another source of data in this case will be the source code, or more specifically the change list or the pull request attached to the bug description when that exists. It's also coming with some challenges that we will mention later. So the conclusion of this slide is that for any data-driven product, it's crucial to consider factors also such as data quality, privacy, security, and intellectual property. And we will discuss that in greater detail very soon. Okay, so the third approach is about approach identification. And techniques that we could use to, in this case, classify unstructured information like bug description. So things like human-based classification, bag of words, for example, based on regular expression, supervised machine learning, or like already mentioned, a large language model, are different type of approach that we could imagine to solve such classification problem. So now the important or interesting part is to determine the most appropriate approach. And it's typically beneficial to conduct some kind of initial feasibility and risk assessment. And here you have a simple example of such assessment. It's a summary of it. So on the right, I have gathered some general data characteristic and various constraints, such as F5 policies and the fact that it's a project without funding. It's basically a side project for me. So from the data, it becomes very evident that a human-based approach would require significant effort and incur substantial costs. We can also analyze that based on the analysis of multiple bugs, it's becoming also very apparent that the unstructured and diverse nature of the existing bug will make the regular expression approach very difficult to maintain and definitively unreliable. Based on the numbers, like the 300,000 bugs in Bugzilla just for big AP, and we have approximately 13,000 new bugs every year just for big AP. it's also relatively apparent that oh, sorry. Yeah, I already mentioned it. So the other aspect is also the fact that we have some classification information with CWE, but unfortunately the number of CWE attached to bugs is relatively low. We have less than 600 bugs that are attached to this kind of classification. So using this source of information in order to build a training data set to train a supervised machine learning system will be very problematic. We don't have enough. We don't have a big enough training data set in order to leverage this kind of approach. So the conclusion is that large language models are probably one of the most interesting approach to solve this issue. One of their characteristics is to provide natively some classification of unstructured text. You just have to define a prompt, and you ask to the system, okay, can you please classify the following bugs description by using this list of category of bugs or class of bugs. And the system will generate or complete a response based on the huge amount of knowledge that has been accumulated during this the initial training process of this LLM. Okay, so but those LLMs does not come without also their challenges, and the first challenge is definitively hallucination. So the fact that LLMs will sometimes just generate invalid or undefined classification for a class of bugs. So we need to deal with that, and we need to find some technical solution to deal with that. Another problem with more with the proprietary LLMs is the fact that they are owned by private companies. So if we and because we want to follow the F5 policies, we have to be very careful and avoid to send critical and sensitive data to them. So we have to find some way to filter out the sensitive data from the original data set. And based on my different experiments, I also observed that open source model that we could effectively run locally or in some private environment are currently not good enough to provide enough accuracy for this type of classification problem in my specific situation. So the next step is about experiment and basic evaluation. So you can, for example, use public data like CVs, or also you can generate some fake data in order to create prompts and test how the system is behaving. So it's an example here of such prompt, and with the generated response from OpenAI, and we see that the response is relatively good. The system is able to detect that the corresponding description is a memory safety bug. So that you can observe that there are multiple issues in the response. So first, the response is not only the classification of the bug, but also an explanation. So it's nice for a human, but it's not necessarily nice for the kind of problem I'm trying to solve. So we can definitively use different approaches to solve this problem. For example, we can do some prompt engineering to force the system to generate only the class of the bug instead of a description or an explanation. We can also use fine-tuning. And the fine-tuning in this case will be to leverage the common weakness enumeration that are available for a subset of bugs. And from this CWEs, there are some categorization, and the memory issues is one of them. And we can use that to train the model to generate, to provide an example of answer that we expect to see for a bug description. There is also another relatively recent option that we could use also to improve the accuracy and more importantly, the format of the response. It's named function calling. It's something that OpenAI released recently. And it was originally released to improve the agent-based or system that wants to basically run some external plugins to generate additional information based on a prompt. So in our case, we could leverage that to ask the system, ChatGPT, to basically generate a method signature containing the class of the bug. And it will be much more easier for us to just decode this output and making sure that the information will always follow the same format. Okay, so to conclude this series of slides, I will talk about now risk mitigation, validation, and deployment. So before using real data, it's important to ensure compliance with AI and ML model assessment questionnaire that the privacy team created recently. There is also obviously the TMA. It's a well-known process now that we have to follow when we create a new system, as well as a third-party security assessment or TPSA if you are using external services that have not been already covered by a TPSA. So this project is not yet fully approved for this various compliance, and this is why I'm still using either public data or entirely fabricated data. So for this project, my goal is to deploy OpenAI models on a private Azure environment, leveraging the existing trust partnership between Microsoft and F5. I think it's an important aspect of the project because using directly OpenAI will most likely be problematic with during the TMA and with the security and IP team. So to minimize the risk of data leakage, there is an option also on Azure that you can enable, and I will opt out of the Azure logging and the human review process typically used by Azure teams to troubleshoot customer environments. I'm also working closely with the big IP team to implement filters to exclude sensitive and critical data from the dataset. There are some additional and more advanced options that I will most likely explore in a second phase. An example of it will be to run the entire pipeline on confidential VMs that will basically encrypt end-to-end the information that I will send to the model. So there is no way for Azure folks to basically see the type of information or the nature of the information that will be sent to this during the inference. So regarding the optimization and validation, I'm exploring various prompt engineering techniques. Some of them have already been presented by Saxon in a previous presentation, so I will not talk about it too much. I will also investigate fine-tuning based on the technique I mentioned before. So basically using the fact that some bugs are attached to common weakness categories. And I will use that to improve the accuracy of the model. And regarding the validation process, it's still at an early stage, so it's definitively a super important step. And right now, I intend to use a relatively well-known machine learning validation process like trend test split and McNemar's test. So regarding the deployment, I plan to generate reports and dashboards that can be accessed at any time. And I think that will be a nice incentive for people to improve the overall process, to test new approaches and so on. And I'm also considering to keep the human in the loop to increase the accuracy of this system in order to mitigate the risk of hallucination. And this approach will be similar to the one presented by Jordan in the upcoming presentation. Thank you. Jordan, I can give you the...
Yeah. Thanks, Laurent. Get started on my screen share and then all right, audio and video test. You can see my full screen and hear me correctly?
Yes.
Awesome, thank you. All right, hello everyone. My name is Jordan Zebor. I'm a distinguished engineer here at F5. And today I'm going to be going over my example use case, which I've named the bug sniffer. For fun and kind of in the spirit of Greenhouse Focus this month, I used some generative AI to create some logos for this project. You can see that it's varied results, but the prompt is like, give me a bug sniffer logo with multiple bugs in a box, make the say bug sniffer. You see it tried. Today, my objectives are really to highlight my specific use case and hopefully inspire others. My agenda will go over the problem space, talk about some of the details of the project as it's going along now, and then I'll end with the challenges and next steps. But first, I want to start with a story on the inspiration for this idea. So one of the most epic vulnerability finders at F5 wasn't a developer, wasn't a penetration tester, didn't have a coding background, and didn't really even strictly study security. She was a release note writer. Now, this person would find vulnerabilities by reading the text comments of a bug, applying a security mindset, and then raising an alarm to the security team when bugs had patterns that matched those of a vulnerability. And in doing so, she greatly reduced the risk to F5 leaking vulnerability information out to the public many times over. So the bottom line is that this person found vulnerabilities just by reading natural language, nothing to do with reading programming language. And ever since then, I've thought like there has to be ways that we can scale this process using machine learning with natural language processing. So we can kind of let the machines do the heavy lifting and find vulnerability bugs that are in the system that maybe aren't classified as such. So the problem space that I'm dealing with here has a few different dimensions to it. The first is that vulnerability bugs contain sensitive details and we need to handle them carefully. So for the uninitiated, a vulnerability really is just a defect, can be in software, can be in hardware, can be in design, and that defect has some security relevance to it. Vulnerability bugs end up being some of the most important bugs for F5 and for our customers because information security time and time again falls at the top of the list of priorities for organizations. Now, vulnerabilities are great for attackers, great for malicious actors, because what they want to do is they want to exploit a vulnerability so that they can compromise either the confidentiality, the integrity, or the availability of a system. In other words, security is important, vulnerabilities are bad, so we need to treat them with a specific sensitivity. And a particular concern for us is that mislabeled bugs can be a problem for us. The problem they present is that when a bug is mislabeled, say the bug is really a vulnerability, but it's labeled as a defect. What can happen is that if we fail to catch that early in the life cycle, there's a chance that that bug could be published to our bug tracker, which is F5's externally facing, completely open database. Now, for vulnerabilities, we are very careful with what we published to the public on those details. But with a bug that's misclassified, we don't have the same level of rigor. So the risk here is that if we fail to catch it and it gets published to the bug tracking database, this is especially valuable for attackers, and especially valuable if the text contains what we call it the recipe, like the recipe for the attack. And we never want to leak the recipe for our secret sauce, right? The second dimension of our problem space is that applying a security mindset and finding vulnerabilities at scale is difficult. So a general reality that we all face is that not everybody has the same level of understanding or applies the same security mindset when it comes to looking at bugs. How this plays out is sometimes developers will file bugs that they see as a plain old defect, and that turns out to be a vulnerability. Now, in nearly all organizations that I know of and have observed and have worked in, the product engineers always outnumber the security engineers. And there's like industry reports that say it's 1 to 100, some say 1 to 80. Either way, my observation at least is always that there are less security specific specialized engineers than there are of product engineers. And because of this disparity, security engineers need to find ways to innovate and find force multipliers to keep up with this deluge of security related issues that are brought up on a daily basis. Then the last dimension of the problem space, as I think about it, is that we have many source code scanners that exist to find bugs in source code, in programming languages. But then we rely on humans to manually review natural language descriptions of bugs. Now, while the tools we have provide decent coverage, you remember that security is about defense in depth. You never want to rely on a single defense. You want to build up multiple defenses and assume that some may fail. So in theory, and many times actually in practice, the more layers in your defenses, the more difficult they become to breach. And by relying on manual review of natural language, we're missing out on some of those bugs. At this point, maybe you're asking like, okay, don't care. Why should I care? Hopefully you're not, but if you are, the first assertion that I'll make is that security companies exist because they're there to reduce and or eliminate risk. They do not add to it, right? And so if we can't find vulnerabilities at scale, some vulnerabilities will leak to the public. We have had this happen before. And if we leak details of a vulnerability, whether it's unfixed or not, especially if we leak that recipe that I said earlier, attackers will take advantage of that. In the best case scenario, this becomes like a reputational problem for us with our customers. They may ask questions like, how can I trust F5 will keep my data safe if they can't even properly manage their own? I think that's a legit question. I would ask the same thing. But in the worst case scenario, something that we publish contains detailed attack patterns, that recipe, and those details are then used to attack our customers. And that can turn out to be very bad for our customers, bad for us and our reputation, and it can cost across the board, customer and F5. So for me, I really care about both those scenarios, the best and worst case scenarios, and I want to try to reduce risk across the board here. So my overarching question is, how can I reduce risk? How can I reduce the risk of leaking vulnerability details? Because this greenhouse initiative, more focused on AI, machine learning, I asked two more specific questions. The first is, can I use machine learning to classify bugs just based on their text? And if I believe that I can, and I believe that it can improve our processes and it can scale our activities, and I believe that in doing so, it reduces our risk, then the next question comes, well, what fits the problem here? What kind of machine learning should I use to fit the problem? Now, during the research phase, and before actually even working on a POC, I submitted the model impact questionnaire, as Laurent had mentioned earlier, and that was disclosed what pre-trained models I was going to use, the data I was going to use, and what safeguards were going to be needed. As this is like a research project where the data isn't being used to automatically inform critical systems or decisions, it's just mostly for me and my experiments, the questionnaire was quickly reviewed and approved. So digging a little deeper into the technology here, this is a natural language processing problem. So large language models and a classifier seem to be the right approach. They seem to fit well. The large language models fit this approach because they support a few things. They support the contextual understanding. And what I mean by this is that I can take massive amounts of raw text, these bug comments, sometimes they're 100 comments with a lot of text inside of it. I can take that massive amount of raw text and I can turn that into a feature set. They also support what I call adaptive learning, which to me means that I can take a pre-trained model. In my case, I took a Roberta pre-trained model, and then I fine-tuned it with all the bug data that I had collected. And I collected about 20,000 bugs. And then I fine-tuned this Roberta model, making it adapted to my specific use case. And because I have bug data that has existing labels on it, so some are defects, some are vulnerabilities, some are crashes, this is a supervised learning problem. All the data has a label, some are vulnerabilities, some are defects, but it has that label on it. So it's supervised, it's already labeled. Now with the classifier working with the large language model, and this is kind of a mouthful, I have a supervised, discriminative, single label classifier. And so supervised learning, which I just covered, is like about the labeled data that I already have. The discriminative part is I really just need to be able to tell the model and the classifier to distinguish between different types of bugs, different categories of bugs. I don't need it to be generating anything like a generative system may. I just need it to discriminate and categorize different bug types. And then the single label classification part, that's about, there's really only one label that should fit for that bug. Now there may be different confidence levels on, something might be 80% of vulnerability confidence level and 20% of defect, something like this. But really in the end, there is only one label that I'm trying to label this data with. Before going through and doing the implementation POC of code, I wanted to think about what does the workflow look like? What does my ideal workflow look like here? And so this is a kind of a high level example. There's a lot more detail that can be unpacked in these boxes, but at a high level, you have your training data collection. So for me, I have like a scraper that will go and find bug data out of public and private samples. So both internal Bugzilla and public ASCII5 data, which by the way, I already have complete access to this data and I'm already threat modeled based on another system I use to have access to this data. So I've already gone through some of the security requirements that I need to. Then as I take that data, I train the model and using the methodology Laurent had said with a train test split the data and then train the model on some and then test it on others. When that model is completely trained up, then on a nightly basis, I plan to scrape for new bugs that are filed every day, compare those labels with my model, which will help me classify whether the bug is a vulnerability, a defect, a crash, whatever. And then in the fourth box, have a queue where the mismatches go so that we can have a human in the loop. Because the important part is we cast this broad net, we find out where are some of the mismatches, and then the humans need to come in and apply their security mindset and figure out, did the model do the right thing or the wrong thing? You know, security issues sometimes are very nuanced. And so it's important in my case to keep a human in the loop. Right now, that human is me, but I think that we can scale this as we move forward in the FI cert team. As far as measuring the results, I'm still trying to figure out the right approach. So I don't really have many conclusions that I can give you that are like scientifically based, but here are some examples of approaches that I'm considering taking to review the effectiveness of the model so that I can answer some of my initial research questions. The first and probably the simplest to implement is what's called an accuracy measurement. So this is pretty simple to measure and simple to implement, but it has a weakness in it that I'm actually running into now, which is when you have a class imbalance, these can be not as helpful. There's a confusion matrix, which will help you to visualize the performance of the actual versus predicted classifications. It's not really hard to implement, and it's a little more difficult to interpret than just the single accuracy measurement, but nevertheless useful. You can see I gave a little example of what it is on the right-hand side, where we have the matrix of actual and positive and negative versus predicted positive and negative. And then the last, which is something I'm still learning about and how best to implement for the measurement, is what's called the precision, recall, and F1 score. As I understand it, these can excel in cases where you have what are called class imbalances, which I'll unpack a little bit in a minute here. And that's currently my reality with the data set. And then also, because the cost of false negatives in my case is kind of high, then I think that optimizing for recall in the F1 score makes sense to measure it. Again, I'm still figuring out what the best way to measure it for my use cases here. So these are just ideas at this point. If you have other ideas, I'd be happy to discuss them with you. So as far as drawing conclusions, I'm still figuring out the right approach on measuring results. So my conclusions are just based on my observations thus far. So my preliminary results are that, yes, I can find mislabeled bugs. I've actually, just in the experimentation phase, found 6 bugs that were misclassified. They were defects or action items or improvements, and they turned out to be vulnerabilities. So at least since I've trained the model and done some experimentation, I've reduced the risk out of 5 by 6 bugs. One of them, an embargo vulnerability, so that's good. But again, I'm not at the point where I can give you a really scientific result and what my conclusions are. But I think that this will help us. Some of the challenges I'm running into, well, there's a class imbalance. You can see my distribution of data. There's about 14,000 defects I have in my training set with only about less than 1,000 vulnerabilities, which not the best for me. I need to figure out how to balance that out a little bit. There's resampling and downsampling and different things I can do there. My computational requirements it's pretty high. The training on the laptop takes about 60 hours per session. So while that supports me locally, I need more power. I need to be able to train these models and iterate a little bit faster. So I'll be looking to figure out how to overcome that challenge. And then a big challenge I think many of us will run into is going from laptop experiment to production use. There's a big gap there in terms of the iteration that you need to do in terms of tuning your parameters or adding new training data to the set and making sure that it has the same accuracy that the previous model did. And then just last, the next steps for me, really refine the measurements of my results so that I can draw accurate conclusions, overcome some of the challenges, and then before operationalizing the model, perform a threat model assessment. So I have an existing threat model assessment for the system this is going to be integrated into. As a security engineer and professional, I'm always looking to identify threats during my design and build phases, but certainly the threat modeling will expose this project to a larger audience who will help me to get the assets, threats, and mitigations really defined and figured out. And then last but not least, the next steps are find more vulnerability bugs faster and reduce risk across the board. That's it for me. You can ask questions through the Zoom Q&A panel or contact me directly. Thank you.
Thanks, Jordan. Aditya, you can take it away.
Madit.
As Aditya is pulling up the screen, which there it is, I will be quiet. Aditya, it's all yours.
All right, thanks, Madit. I appreciate that. Thanks, everyone, for attending the talk today. I hope you guys are having a great time. So let's take a look into the AI accelerated cybersecurity play. So in the next 30 minutes, with my team, Amit and Bharat, so we're gonna discuss about some of the research that we have published recently and where we have started and where we have gone into. The message that we want to deliver is like for cybersecurity and the way threats are expanding these days, we really need AI acceleration to solve cybersecurity challenges. So that's a transference from the process of designing robust machine learning algorithms towards generating the cybersecurity defenses using AI acceleration. So let's get it started. So before moving further, let's take a look into the challenges that we are facing these days, right? So it is related to the data. So data is the key component which everybody needs. When I use the term everybody, I mean from attackers to adversaries and to the organizations as well, which are developing security solutions. Because that's where you're going to get the context and that's where you're going to get the complete flow that what exactly is happening as related to the workflows, related to the security issues and sort of things like that. So some of the stuff that we have highlighted here is related to the media taglines, and you can clearly see, why data matters these days, right? Of course, we've been processing data for long periods of time, but these days with advent of AI, why it matters, because the context matters and the output also matters. So with that, if we are talking and living in the world where data is expanding rapidly, we're not talking about gigabits of data, we are talking about petabytes and terabytes of data at the moment, right? So from the security point of view, attackers are also evolving, right? They want to control your data at any cost. That's why stealing of sensitive information, frauds, bot attacks and all things, they are increasing at pretty rapid rate. Even if you talk about ransomware, right? The idea behind that attack model is very simple. We're going to control your data, we're going to abuse it, and we're going to get some money exfiltrated out of it as well. So that being said, so if you look at this snapshot, the biggest data breaches that are happening, so it is being, again, exponentially rising, and organizations need to really take a look into how they are going to make sure they are secure, they are protected against the threats, and they are circumventing the breaches, right? Because that's the most important part to avoid the brand damage and all that. But the primary point that I want to highlight here is that is the data, right? So whoever going to control the data is going to control the keys to the kingdom. With that, we are expanding the discussion on this part, right? What are the challenges that are associated with data and why scalability is desired, right? Okay, you can actually build some, standard heuristic approach, and you can also build some signatures, but the things need to scale with passage of time. And why I am highlighting this, because if you see these days, right, the way devices are exploding and the way communications are happening, look at the volume of east to west traffic and north to south traffic, and even from app to app traffic, for example, right? We are living in the world where our data is being moved before we even think about it, right? And that's the world we live in. So it means we really need to make sure that how we handle this data problem. As we discussed, security breaches are rising at a significant rate, and we really need to have some kind of security defenses in place that can actually act accordingly, which means like they have to act fast as well. Another problem that are associated with the data is like increased log collection, right? This is outpacing analysis because we are collecting heavy sets of data, from every device on the network, every mobile device that is moving, movement, cloud infrastructure and everything, right? So data is being collected at large scale, and we are not able to analyze it very efficiently, right? And that's why we really need to move towards cybersecurity play, which are having an AI acceleration to the core. Of course, we talk about vendor solution integration complexity is more of a strategic play because you have many solutions in play that are also an issue. their integration, how the data needs to move from the one device to the another, one platform to the other. And of course, as I discussed, the cyber threats are evolving at an exponential rate. We are moving towards an entirely a different world. We're not talking about AI-based threat model these days. So again, data is the key. So what we really need to make sure that, some of the machine learning algorithms that we have developed earlier, how we really need to make them scalable. So these are some existing challenges. And why it matters, right? What are the advantages that we're gonna get from transferring, designing machine learning algorithms, but also having an AI acceleration support to it? Speed and scalability, that is definitely needed. We just cannot, sit there and waiting for a couple of minutes so that our, solution process the data and give us some output. Until that point of time, I think we lose the touch. So speed and scalability matters a lot. Superior predictive intelligence. We want to predict the attacks upfront, right away, right? We just don't want to sit for a longer period of time and, waiting for things, or data processing is going on and sort of things like that. We need superior predictive intelligence. Like before the attack even started, we just need to assess our controls. We just need to assess what the security posture is and make some really good intelligence points. Of course, we need to formulate vital priority decisions. It matters because we have to prioritize the threats, right? We just cannot go along, in the process of handling all the, security risk scenarios in a one go, right? That's not possible. So we really need to have some vital priority decision to be made. And that usually is in line with the proactive risk predictions as well, right? So what is the risk associated with my edge, right? If I've deployed it in a certain cloud environment. If I'm deploying, from VMs to containers to now, functions, right? So what are the risks associated with that? That's just one example I'm highlighting, but it's like a risk predictions. We really need to get it upfront. Also, it matters how fast and efficiently you are tuning your machine learning algorithms based on the output that they have thrown to the audience, and to making sure there should be a self-learning capability, because that's how we process the context, which leads to further maturity, right? If our machine learning algorithms are not going to be mature with passage of time, I think they're not going to learn efficiently, but we need that. Of course, we need a prescriptive insights and analytics, which is just like data processing need to be happen in a reliable way so that we keep on getting insights, some intelligence points that we can feed into the other parts. So until right now, we discuss about what are the challenges associated with cybersecurity, what kind of data that we are handling these days, and why we really need AI accelerated cybersecurity. So moving further, so I'll take a quick, 2-3 minutes to highlight the data sets that we have used in this whole research, and what is the use case we have targeted, and why we have stuck to this specific use case, and we have extended our research through multiple papers that we have published. So the problem and the data set that revolve around for this is related to the DNS threat use case. It's a domain generation algorithm. I think you must have gone through it earlier as well. So I'll take a quick 30 seconds to highlight it. The process goes like this. A user visits the malicious website, malware is installed on the end user system. The malicious code in itself has some kind of algorithm embedded into it that has the capability to trigger a lot of domain names on the fly, which is dynamically generated. Because this algorithm is being embedded into that malicious code, which is a DGA, the attacker knows the seed value and everything. So it can register one IP address, which is going to be resolved from a one dynamically generated domain name, which we call as AGD, and it resolves. And then the command and control communication starts. So this attack method is very prevalent, and it has been widely used even these days to just bypass the standard heuristic detection, also the standard denial list also in that scenario, to just avoid that thing, right? So you don't need to embed your command and control server IP address or domain name directly into the binary, which you can reverse engineer and find it out. So it's a dynamically way. So how we look at it, this attack on the wire, let's take a look into it. So if we're sitting into the network and tapping the network traffic, so what happens from the infected system? You can clearly see this is an ID IP address, which is a client one, and is resolving and sending a DNS query. So you can say it is here requesting the domain name, which is generated dynamically. And of course, it resolves to the IP address here. So it starts the communication channel. So that's how we see this traffic on the wire. And if you look at the lower screenshot here, you can clearly see these are the domain names that are generated through a DGA during the sunburst attack, right? The way they want to exfiltrate their data once they compromise the supply chain. So this problem is kind of pretty real. So we have invested significant amount of time to just take this thing as a cybersecurity use case and starting from building robust machine learning algorithms and then using AI acceleration as a part. So I think in the next section, I will invite Amit to talk about what we have implemented in this case. And after that, Bharat will actually highlight how we have actually used some of the AI acceleration using Morpheus platform. Amit, please take it.
Oh, sorry. Thanks, Aditya, for explaining DGA and its importance in cybersecurity. The role of AI/ML is pivotal in detecting DGA, and recently our work has published in Network Security Journal, which focused on scalable ML/AI framework to detect DGA. The link of these publication can be found in the end of session. The next slide. So here we are talking about AGD ML workflow, which includes 4 steps. The first step is data generation. Here data was collected using random sampling technique. Here Alexa's 1 million domain are used as a legitimate data, and for DGA, 40 DGA subfamily were used. We use data validation using hypothesis testing and exploratory data analysis. So after these steps, data is clean and ready for using the model development. If you see in the model development step, which is very crucial step, the model was built using traditional algorithms, deep learning algorithms, and finally, assembling of these all algorithms. Here, model was selected based on cross-validation and hyperparameter tuning to avoid underfitting and overfitting of the model. The next step is model evaluation. Here we look for model metrics assessment, which performed by F1 measures and basically ROC curve. So F1 measure is basically derived from precision and recall. Then the time comes to deploy the model, which was done using the NVIDIA's Morpheus pipeline, which enhanced the scalability and throughput of the model intent. And final step is monitoring. Monitoring here, we are observing models' behavior in environment, looking into latency, throughput, and other metrics, logs, and most importantly, feedback loop, which incorporates user feedback to enhance the model's accuracy. Next slide. So the above technical diagram of project AstraML's DGA module has 3 components, basically training, inference, and feedback. As you can see in the left-hand side, the input data having benign and malicious domains, which divided into 2 parts. First one is feature extraction process of the input data, and the second one is domain encoding of the input data. In model training phase, the model was trained using the 2 ensemble models. The first one is ensemble of traditional algorithms like random forest, which is a bagging ensemble models and try to reduce overfitting, whereas gradient boost, which tries to reduce the bias. Here, the voting classifier is used to ensemble the above models. We are using the soft voting, which takes average of prediction probability from above models to infer the final probability. In deep learning model training phase, deep learning model use such as LSTM, CNN, 1DS, and CNN max pooling use. CNN is basically convolution neural network. Deep learning algorithms commonly used for text analysis and natural language processing tasks utilize convolution to capture local patterns and hierarchical learn representation of the text data. Whereas the LSTM is a powerful tool that remembers and understands the long text sequence. So that's why we use both of these techniques. Whereas 1D CNN with max pooling use for efficiently extract important features from the sequential data. For ensemble, we use logistic regression based meta learner here, which trained on the outputs of the above model, which enhance the model prediction. If you see in the right hand side, there is inference phase here, and hereby features are extracted and domains are encoded, and finally the model's optimum threshold of predicting probability were aggregated, and the results were reported in the feedback loop to enhance the model's accuracy. Next slide. So here the table shows the accuracy of different models such as LSTM, CNN LSTM, and CNN with max pooling, and ultimate ensemble that combines all of these models. So F1 measure was used here because it can handle class imbalance data very well in binary classification models. As we can see among these models, F1 measures were highest for the final ensemble model here. These means that combining these models together through ensembling lead to improved prediction. The ROC curve plots used to plot between true positive rates and false positive rates. Basically, true positive rates also called sensitivity or recall, and false positive rate also called a specificity at various thresholds. So these plots were used for that. We found ROC was significantly increased in deep ensemble methods and final ensemble mode. These metrics were consistent across all the platforms we tested, like Vertex AI and GCP and the Morpheus pipeline, meaning it gives the same results regardless of where it was used. Now over to Bharat.
Thanks, Amit. Hello, everyone. This is Bharat. Now we are going to look into how we extended our system with AI acceleration. The accuracy and other metrics of the system developed were up to the mark, but the main issue is with the inference performance. As a typical DNS query takes 20 to 120 milliseconds to get the response. Even after several optimizations on our TensorFlow and scikit-learn based implementations, inference rate is still low to use in real time. Then we explored OnNext, which improves inference speed through optimized and hardware accelerated OnNext runtime. But it is still not enough to handle high input flow. This is where AI acceleration solves the issue. We have used NVIDIA's Morpheus in our inferencing phase. We'll see how it significantly brought down the latency and increased the throughput. Morpheus is an AI cybersecurity platform which is open sourced and developed by NVIDIA to build faster and more robust end-to-end AI pipelines for security use cases. It is built from the ground up using the EGX stack and rapid libraries. It supports multiple deep learning frameworks and utilizes the inferencing power of NVIDIA Triton. Next slide. Here is a short demo showing the performance of Morpheus. We have the Morpheus setup in a GCP VM. Morpheus have various components running on the multiple Kubernetes pods. Triton AI engine processes the inference requests. Kafka broker consumes and publishes messages between various components of Morpheus, with Zookeeper maintaining the coordination with the Kafka broker operations. We have the pipeline code and ML models in the SDK pod. We need to shell into the SDK pod to run our pipeline. Here we are running the pipeline with domains.csv as the input file. When we run the pipeline is registered and built with various stages like setting the input source, deserializing, preprocessing, inferencing, etc. Here the pipeline has a default batch size of 32, for which we are getting an inference rate or throughput of around 24,000 per second. Apart from hardware acceleration, Morpheus uses back pressure, reactive programming, and fibers to optimize the AI pipeline. We can try with different batch size. Here is a run with batch size of 256. The throughput increased from around 24,000 to around 50,000 with an increase in batch size. We can take advantage of larger batch size to serve larger networks. Next slide. Yeah, now let's take a look into the numbers. Here is a comparison of Morpheus with other frameworks running with similar system configurations. These metrics are for batch sizes 32 and 1024. So here we can see how efficiently Morpheus is performing compared to others. We can see Morpheus on the right of the tables having least latency and highest throughput. And we have the graphical representation of the throughputs showing the magnitude of the difference, which is exponential. We have significant performance improvements. This helps us run our solutions in real time. Next slide. FI can harness AI acceleration to efficiently deploy ML-AI solutions in the production environments to achieve acceleration and process extensive data in a distributed manner to generate faster inferences. Cost saving is a must through optimization. The latency and throughput results validate the same. This work also highlights how we can advance FI cybersecurity solutions requiring large-scale data processing in real time, detecting and mitigating threats at scale with speed. Additionally, the work shows how AI acceleration can help design next-generation cybersecurity solutions that require power and processing for cloud and on-premise deployments. For the future use cases of generative AI, this work can help decipher how the AI algorithms can be deployed with more efficiency and scalability by selecting robust architecture and AI frameworks. Next slide. Thanks, and we are open to questions. Here are the links to our research. You can check it out. Thank you.
Thank you, Aditya, Amit, and Bharat, and also thank you, Laurent and Jordan. I know we're reaching time, but if there are questions, please put them in the Q&A or via chat or via email. And our hope is that the examples that the presenters showed you today, that you find them inspiring and will think of your own ideas and submit them during the Idea Fest, which is going to run for several weeks. If you submit ideas with respect to how generative AI or AI in general can help in increasing your own productivity or help improve the product, or let's go for it, create a new line of business. We have a whole month to improve on those ideas and make them actionable. One more thing to keep in mind, the security and legal issues are all being worked out. At some point, there will be a sandbox with appropriate TMAs and TPSAs, the threat model assessment and third-party security assessment, available for people to experiment in. While that is being worked out so that we don't get left behind, it's very important for us to ideate. And that is the whole vision behind the Idea Fest. And again, these are some example use cases. I hope that we get some from the audience. Thank you. Back to you, Fida.
Thanks,
Oh,
Peter.
there are questions in Q&A. We can stay long and answer them. Aditya, there's some questions for you. If you like, you can answer them in Q&A or you can talk.
Yes, so let me go to the first question.
So the first question here is for you, Aditya. Would this create immediate efficiencies to Shape's infrastructure?
Yeah, so I think looking at the very first point I want to highlight here in this case is that, we did this research as an independent study highlighting just not to be strict to one specific product in the case. So we just want to see how exactly things improve with new, models and deployment and the AI acceleration. So the question that has been asked on this part of the Shape, like we believe that we really need to first assess the scenario of the kind of machine learning algorithms that we have already using. Can we make a structural change in those algorithms based on this research? If we can, we believe that there will be definitely improvement in that part. Looking into the AI acceleration part, so our independent study highlights the fact that, with the NVIDIA Morpheus, there are other platforms that we have also tested, like libraries, other ones that are supported ones. So we can also look into that perspective, moving from the one step to the next step, like how things are improving and to what extent we can manage the cost accordingly, right? There are definitely, when you say AI acceleration, things are there. But this is just not only a one part of it, what we are highlighting. It's a step-based mechanism, right? From X to Y to Z, right? How much improvement has been made with different kind of thing, like if you're using ONNX, if you're using other parts, right, the combination of it. So that's how it actually reflects it. But yeah, how basically looking into the F5 products, we believe that, the scalability needs to be, enhanced. And I think just it's a better way to just take a look at it and see where we can go from there.
Next question for you is, what's the marginal cost of running an ensemble of models? Would this have practical applicability to commercial enterprise like F5 for security use cases?
Yes, so I mean, generally looking at the if you ask us the specific number for doing the cost evaluation, I think it's still this work as in process at the moment. But what we have seen in this case is that this is what we have to assess, right? How fast we want to opt in, or in relation to the cost that is incurring to us, right? As I restated right now, right? So we just not only tested NVIDIA Morpheus, so we go step by step from CPU to GPU combination with ONNX and some other libraries, Scikit and everything, combination of that. And then we reach up to the NVIDIA Morpheus. So every step through that, we believe that there is an enhancement, which means like there's improvement. And now that it comes back to our product teams and us, like we need to assess to what level we need to balance it out with the cost as well as the improvement, so that it just don't incur too much cost to us, but also it just process and provide a scalable solution. So I think that's remained to be checked in that. And we believe that this results actually gives some intelligence points to highlight that aspect of it.
And I see another question, I believe it's asking, what are the DDoS and BDoS use cases?
Like, so DDoS use cases, and that depends on I would like to start it from the perspective of how you design a threat model, right? So if we talk about a DDoS threats that are happening at a layer 7 or at the other layers, right? So first we really need to analyze like what kind of cybersecurity problem we are solving. So if we are actually looking at a solution that is requiring a data to be extracted from the network, traffic, and then making assumption on the base that here we got that data and we are seeing these kind of lot of north to south traffic that is coming up, right? It's hitting our servers. And then you extract that data and process that data, right? So it needs to be processed faster to get, inferencing and then the results, right? But again, it depends on the kind of cybersecurity problems that we are solving. As a part of this research, we are primarily focused on where we have a lot of data sets as well, and data that has been extracted from whether it's from the network or from any kind of logs and all those kind of things. But in case of a DDoS solution, I think it also depends on the fact that how we are actually, stopping those kind of things, right? What is the core model of our cybersecurity solution for that? But as long as if we are extracting data from the network flows that is hitting our servers and we are just doing the intelligence on the top of it, I think it works pretty well. And even apart from any, for example, layer 7, right, HTTP traffic, all this research can be applicable there as well, based on, like, for example, in a WAF, right, we're trying to build threat score for a malicious client, right, in adding to whatever the, attacks that are coming from those end user systems to the applications, right? So the more the data you have, the more you can consume the things, and efficiently you can actually provide better results.
Thank you, Aditya, Amit, and Bharath. There's a question Mudit will answer. So for future post-idea stage, is there an option to have a stash of loaner, high-powered loaner laptops for people to experiment with?
Thank you for asking the question. That's a cool idea. We will keep it in mind. We hadn't thought of that, but there are some sandboxes where people can experiment in the making. As I said earlier, they're going through a TMA and TPSA, and after that, they'll become open to people who want to experiment. So, but it's a cool idea, Christine. Thank you for asking that question. Rather than loaner laptops, there is some thought around getting on-premises servers with GPUs, but this is early days. So let's see what kinds of ideas we get in our idea bank and what kind of experiments we need to run. And then we'll evolve the sandboxes.
Thanks, Mudit. And I see one more question. I believe it's directed towards Aditya. So does the age of data influence its value?
Yeah, definitely. I think it's a very good question. It's a very tactical one, and I will answer it in a 2-3 different points. Just try to cover the best that I can. So considering that value data with the passage of time, as we say that data evolves, right? And it is entirely related to the kind of technologies and the advent in security that is taking place. So for example, in case like if we are building a model, taking a data set of a 2016, right? That is like some sort of like a DGAs, and that time is like very specific ones, differential ones. But with the passage of time in the next 7 years, things have evolved, right? So data has intrinsic value. We want to hold to some of the, the features and the output that we have got from data, but we have to continuously iterate our machine learning algorithms with the new data sets as well. So if you remember that when we're presenting that a complete model, the way DJ is working, you can see there is a feedback and a loop mechanism there as well, right? So that is also which makes the machine learning algorithms much mature with passage of time. And we cannot stop it, right? We cannot stop, hey, I have this data set for, from this year 1 to year 2, right? But we have to improve it. So this is actually pertain to the fact that the more you have to grow with the passage of time, when I use the term maturity and effectiveness, it actually relates to the fact that we need to make our machine learning more mature by feeding that with the new data sets that are popping up, which is going to come from the security and threat intelligence that you're going to conduct as a part of your research. But actually, you have to make them grow. You have to make your machine learning algorithms grow by continuously feedback and the process that needs to go, which is like updating it with the new data sets as well.
Thank you. So Muda, I see you're typing an answer to one of the questions. You're free to continue doing that. Okay, it's closed. Thank you. So I think this wraps up session 2. We appreciate you attending and tuning in. Thank you to Aditya, Bharat, Amit, Laurent, and Jordan for presenting today. Really insightful discussion and findings. Our next session in this training series is this Friday, session 3. We'll have Ken Aurora present on AI for both product and process improvement. So there's a registration link in the Greenhouse Idea Fest website, but also we'll send out the invite sometime later today or tomorrow. So thanks so much for joining. We appreciate your engagement, and we hope to hear from you throughout this Innovation Month with your innovative ideas and in future sessions. Take care. Have a great day.
Thanks, everyone. Thanks, Mudit. Thanks, Rita.
everyone.
Great work, guys. Take it back.